Welcome back, everyone, for the Western Hemisphere Virtual Symplectic Seminar. We're very excited to have Basak Gurel tell us about topological entropy, barcodes, and Floer theory.
Thank you. It's good to see everyone, and thanks for having me. Okay, so I'm going to be talking about topological entropy and barcode entropy. That is, a new concept here. All of what I will say is joint work with Erman, Cineli, and Viktor Ginzburg. Okay, so let's get started. So I'll try to. You see this thing, right? I see it, so you see it, I suppose. Okay, so let's start with, I'm going to start with just telling you a little bit about topological entropies, just to set the basis for what is to come. So this is an important basic invariant of a dynamical system, measures complexity of a dynamical system, we could say. And the question that we ask and we try to address in this work is, how can we observe this invariant for a Hamiltonian diffeomorphism being symplectic topologists? How can we see this invariant from Floer theory through the methods of Floer theory, which is not at all obvious a priori. And so entropy, positive entropy, again, we will talk about it shortly, can come from various sources. Some are more robust, like growth of, fundamental group things like that. And some are more fragile, more like dynamics related sources like horseshoe type features. Okay, so, and as you will see shortly, what is key here is that if we want to detect this topological entropy, we need to actually somehow find a way to extract from Floer complex with some amount of information up to an epsilon error. So this epsilon is our precision here, or resolution, we could say. And this information should grow exponentially with the order of iteration as iterate our map. So, okay, so, and we are going to see sort of, obviously a question is whether we have such a thing and how to extract it. This is the question that we try to address. And as I said, let's start with a little sort of discussion about topological entropy. So it measures exponential divergence of orbits, as I said, complexity of a dynamical system. So the way one usually constructs it, it's constructed in the following way. So let's start with a compact metric space. So I have my distance function there. I'm going to stick to homeomorphism. In general, you don't need the map to be invertible. It can be just a continuous map. So what one does is we started with a metric D, and you define sort of the successive metrics, the so-called K shadowing matrix, D sub K, by taking the maximum distance. I'm sorry, I'm somehow lost this thing. Between the iterations of the map applied to our initial points. What this distance does is, so 2 points are going to be epsilon close in this DK metric if they're actually epsilon close in the original metric through K iterations under phi. Okay, so then one may ask the following question. So let's suppose that we are in a situation that we can only distinguish points up to an epsilon error. And so we may ask, okay, how many distinct orbits am I going to be able to tell apart if I sort of follow this orbits through K iterations? So there are here are two ways to do it. One of them is, this is all like standard stuff, the so-called epsilon covering number. You say, okay, let's cover our sets with balls of diameter less than epsilon. And then I should take the minimal cardinality of such a covering of X, and this is called the epsilon covering number. So notice that, I mean, I'm in a compact space, so this covering number, I mean, because it will have a finite subcover, so in particular, this cover will have a finite subcover, so this minimal thing will be finite. Okay? So I need to take minimal cardinality here because it's possible that when I do this type of covering, these balls can actually come close to each other, and I might be overcounting. So you need to take the minimal cover. And an alternative way to do exactly the opposite, what you could do is you look at the so-called epsilon separated number. What this does is you look at the sets which are at least epsilon, you look at sets which we call epsilon decay separated. So distances between points in such a set will be at least epsilon far from each other. Okay. And in this case, because such a set can be really sparse, you may actually miss some distinguishable orbits this way. So you actually need to take the maximal cardinality if you're doing it this way. Okay, and as I already said, the CK is finite, and it's also easy to see the following inequality, that the separated epsilon separated number is bounded from below and above by the covering numbers. So then you define the epsilon, topological entropy by first taking the, first looking at the exponential growth rate of the covering number as you look at longer and longer orbits. And then you want to let your resolution, if you wish, go to 0. So, and this is topological entropy. And you could equally define it using the epsilon separated number. Again, I wanted to do it in two ways, because in fact, the way we define our barcode entropy is more closer to the separated number definition. But the epsilon covering definition is also very kind of maybe intuitive. In any event, this thing, we look at the H top. Maybe it's worth saying, in the first case, in fact, not in the second case, but in the first case, you can replace this lim sup by lim, because this sequence, when I think of it as a sequence in K, it is subadditive, so it has a limit. It converges to when I look at divide by K and look at the limit, it actually converges to its infimum. So we could replace it. Not necessarily in the second version, but one way or another, they converge to the same thing. And this also tells us that if I am to get anything positive here, I need to have this thing at least growing, exponential growing, okay, with K. Okay, so a few things. Of course, in the beginning of everything, there was a metric here, but in fact, it is a topological invariant of a dynamical system. It actually doesn't depend on the metric. Invariant with under conjugacies, topological conjugacies. And it is bounded from below by the Lipschitz constants of the map, constant of the map times the so-called box dimension of the map. I mean, one can think of this as just the dimension for any practical purposes. And in particular, this also tells us that this quantity is going to be finite if you just take a smooth map from on a compact space. Okay, so it will be finite, and this I already said. Some key properties, important properties, that it is localized. So if you take a closed invariant subset, then the entropy you obtain on this set is less or equal to the is bounded from above by the, or it's a lower bound for the entire entropy. And another thing that will be used later on is that it is additive with when you take the product of these two maps. Okay, so examples, for example, if you take an isometry, this will be 0. instance, a rotation. And it all makes sense because you are not changing the distance as you iterate your orbit, right? So therefore, you shouldn't need more and more coverings, for example. And another maybe easy to see entropy is going to be the situation of the so-called doubling map. You can just think of it on S1. So it takes x to 2x. And in this case, it's also easy to see that this entropy will be just log 2. And in this talk, everything, all logs will be in base 2. So log 2 is 1 in this case. And for autonomous Hamiltonian diffeomorphisms of surfaces, it is 0. Okay, not necessarily in higher dimensions, but there is not much room basically to have any interesting dynamics in this case in dimension 2 to create this entropy positivity. Okay, so there can be, particularly in higher dimensions, various sources of this notion, positivity of entropy, but there are two sort of basic things that I want to look at, as I already said in the beginning. One of them is I will broadly put this in the category of things that are coming from algebraic topology. And here the general idea, I think, is that this H top is going to be bounded from below with some kind of homology growth or a fundamental group growth, this type of thing. So if you have exponential growth of free homotopy classes, for instance, is populated by periodic orbits, you will get positivity. And of course, the next situation of this, and more along the lines of, as I said, it provides a lower bound for it is given by homological growth is comes from the so-called Shoup entropy conjecture. Yomdin's result is this conjecture basically says that for any phi, any smoothness, and it falls in the C0 case, but starting C1, the conjecture says that this H top is bounded by the logarithm of the spectral radius for the map induced on homology. Okay, so this is proved on, this is correct and proved by Yomdin in the C infinity case, but it is not known in other situations. As I said, it's known to be false in the C0 case. And here's an example of this situation. If you take a linear map of torus, so it will be given by a sort of matrix with integer entries, then just you can think of the situation of the diagonal case, for example, and it's immediate to see that this H top is going to be equal to the logarithm of the absolute value of eigenvalues greater than 1 in absolute value. Okay. Anything less than 1, again, you won't need to you won't need any new sets to cover your set from the perspective of this covering situation, covering definition. Okay, another source, and this would be more like the one that I'm going to be interested in, I am interested in this talk, is more like the pure dynamics features. In a couple of examples, so when I think about this, I'm thinking of really like you can have localized horseshoes supported in a ball or something. This is where the positive entropy is coming from. So the first example in this case is like this so-called shift map, Bernoulli shift map. So we are looking at sequences here in 2 symbols or n symbols in general. It's just going to change what the entropy is, but it will be positive. So this shift map is you just shift 1 step to the right, that sequence. A Bernoulli shift naturally arises in the case of horseshoes. So many of you probably have a picture of the horseshoe map in your mind. You know, there is the square with the U-band, and you squeeze, you expand, turn it around, put it back to the same region, do the same motion and again and again, and you will have these sort of invariant sets there, and possibly switching points back and forth, and these like horizontal strips in the picture in your mind. That's where this shift to map arises, the symbolic dynamics in the case of like standard horseshoes. But in general, horseshoe is basically something, well, I'm thinking of horseshoe as an invariant subset, a close invariant subset, so that when you restrict the map to that set, it should be some power of a Bernoulli shift. Roughly speaking, this is what it is, basically. But they are in abundance. This is the point that maybe I would like to make. And C infinity generic in dimension 2, for example, and finite genericity, I think, in higher dimensions. And a key feature of that is that, in fact, all the entropy in dimension 2 comes from horseshoes. Okay. And once more, you can have this entropy really coming from like a tiny, tiny ball, basically. It will capture everything. And what we are trying to do is really, is nothing, has nothing to do with like this large scale geometry or anything. We are trying to really see this entropy coming from this tiny set, if you wish. Okay. So now let me introduce the main sort of concept here we're going to be looking at. So barcode entropy, but before that, for the purposes of this talk, let's just suppose, I mean, in the work altogether, we always work with smooth maps, and this is absolutely essential. And smoothness in this matters, particularly in dynamics related questions, matters a lot. I mean, we in symplectic geometry always work with smooth maps, don't usually, okay, there is C0 symplectic geometry, of course, that's a separate thing. But in dynamics, these are really sort of important things. In my case, everything is obviously smooth in the C infinity sense. And I'm also going to assume like everything is non-degenerate, all intersections are transverse, etc. So one can give more general definitions than to a certain extent. We do this in the paper, but it's just, let's not worry about any of this. So I'm going to be working with the monotone symplectic manifold. Somehow lost my pointer. We can assume it to be closed for simplicity, but it doesn't have to be. Perhaps I forgot to emphasize in the beginning, I should have said it, we are trying to capture this for compactly supported Hamiltonian diffeomorphisms. So in the, when I phrased the first question, I probably haven't emphasized it enough. We are looking at Hamiltonian diffeomorphisms which are compactly supported. Okay, so this is really not the case of, rep flows, this type of thing. Okay, so then for this reason, actually, it doesn't have to be closed, but we can just assume it is to be for now. Lagrangians are going to be closed monotone and Hamiltonian isotopic to each other. And we're going to look at the Floer complex coming from the intersection of these two Lagrangians, and in particular, the barcode of coming from this complex. I will say a few words about the barcodes, but one can just think of it as like arrows connecting these, for instance, in the intersection points, but they will be a bit more decorated than that, carrying a certain amount of information. So, and then in the barcode of this complex, let's look at the bars of length greater than epsilon. So I'm looking at, if you wish, essentially Floer connecting trajectories which have energy at least epsilon greater than epsilon, roughly speaking. And the key property actually, which is essential for all of these things, is that this quantity gives a lower bound for the number of intersections of two Lagrangian submanifolds. And it's essential that I have this epsilon thing here. And this is like, this intersection, moreover, is, I mean, and this number is fairly sort of insensitive to epsilon perturbations. It's Hofer stable, okay? So, and we have this exact sort of inequality, how the two are kind of how it bounds from below the number of intersections we have. Okay. And let me set, whenever you're seeing the talk L to the k, it will be like the Hamiltonian image under the kth iteration of our Hamiltonian diffeomorphism. So let's define our main concept here. So first, relative barcode entropy. This is the case when we have a Lagrangian and I'm looking at its iterated images. So first of all, the epsilon barcode entropy is going to be the exponential growth rate of the epsilon barcode. Okay, so it's very similar to the definition, if you wish, to the topological entropy. But as I said, because I'm looking at barcodes of length greater than epsilon, it's more like analogous in some sense to looking at epsilon separated sets. Okay, so, and then you take the limit. And then we want to take the limit as epsilon goes to 0. Okay, so, and this is what we call the barcode entropy of phi. So now we want to have the Hamiltonian version of this. And what you do is just take this whole picture, look at this symplectic product, and for the Lagrangian, which is take the diagonal, then you look at the barcode of the iterated complex there. So this gives us the absolute barcode entropy, first in the epsilon barcode entropy, and then the absolute barcode entropy of phi. Again, the Lagrangian construction, just take this Lagrangian to be the diagonal in the product. Okay. Well, again, in dimension 2, this is going to be 0 for an autonomous Hamiltonian system. And yeah, I mean, I have these remarks in particular because things are a little frustrating here, because a topological entropy have a lot of properties, and a lot of this, I mean, one may ask the same kind of questions for our barcode entropy. And it has a lot of properties, except almost none of them follow from the definition beyond the simple things. So this is one remark. And another remark, the Floer complex, when we the Floer complex we are working here in all of this business is where we consider all homotopy classes of orbits. And this is important because positive entropy can come from non-contractible things. So if you just stick to only contractible orbits, etc., your barcode may be 0 while you really have positive entropy. So if we want to really capture this, we have to work with, it's important to work with all homotopy classes. Okay. So let me say a few more words about barcodes here. So we have heard a lot of talks, of course, in some previous sort of seminars about these things. These were, put in the sort of forefront of symplectic geometry by Polterovich, Shelyukin, Asher, Zhang. And actually, our work draws heavily on the way Asher Zhang developed this machinery. And the complexes, as I said already before, will be generated by intersections. We work with some universal Novikov field, and it is important that we have an action filtration over that. So, okay, in order to define what a barcode is, let me introduce this concept of singular decomposition. So what you do, a basis for this finite dimensional complex is called a singular decomposition if it has the following formula. We have this alpha I, eta j, gamma j, and so we have the closed forms that gives us the infinite bars and give us the homology. And then we have the ones that are, that are eta, sorry, image of the boundary map. Okay, so etas are hit by the gammas. So this type of a very specific type of basis, and that this basis is orthogonal in the non-Archimedean sense. So the action over a sum of such things is picked up by the maximum action of each summand when you take the maximum. Now what we do is, so maybe before I say what we do, Asher-Jank actually proves that this complex admits a singular decomposition, and it is the barcode you get there is going to be independent of the choice of this decomposition. And what is the barcode? Well, okay, what we do is we just take these pairs, look at the action difference, and sort of we can order them in this way, okay? And this increasing sequence of finite bars, so this will give us the finite bars, and then there are the infinite bars that are coming from the alpha piece of this basis, or this singular decomposition. And so this will be the infinite bars. So the barcode will have the finite and plus the infinite bars. Okay, so here I just, for, I've been already saying that the key feature of this barcode business for this work is actually they provide the lower bound for these intersections. I just wanted to write down what it is in the non-degenerate case, in the transverse case. This is the dimension, and then you get exactly this. So here, this BLL prime is the number of barcodes in the complex. And it is greater or equal to this, and which is of course greater or equal to our epsilon barcode entropy, where we look at only the bars of length greater than an epsilon. Okay, so now I'm ready to state results here. So the first theorem is, there will be three theorems. The first theorem says the following thing, that this entropy, the barcode entropy, I have my closed monotone Lagrangian submanifold. The barcode entropy is provides a lower bound for the topological entropy. Okay, so it's bounded above by the topological entropy of phi. And because of the fact that the entropy, topological entropy, is additive, and the identity map has zero entropy, we have this equality, and therefore we obtain in the Hamiltonian case that the absolute entropy is bounded from above by the, the barcode entropy is bounded from above by the topological entropy. Okay, so in particular, it tells us that because I already said that for any sort of smooth map, anything that is Lipschitz, it's the topological entropy is going to be finite, and therefore the barcode entropy is going to be finite. Furthermore, the epsilon barcode entropy can grow at most exponentially. Now, this is all good, but at this stage, of course, we have this H bar bounding H top from below, but it is still possible that this quantity could be zero. which then, would pretty much make the first theorem useless. So the next result shows that this is not the case. So to this end, let me introduce this concept of a locally maximal set. So a locally maximal set is a compact invariant set, so that in a neighborhood, it is the only invariant set for the map. So if it is, sometimes this is also called an isolating neighborhood. So if you have, for instance, it has a neighborhood so that if you have a point there with a full sort of orbit contained in this neighborhood, in fact, this point, this whole orbit and the point has to be in K. Okay, so this is what that is. And the theorem is that if we have a Hamiltonian diffeomorphism for a closed monotone symplectic manifold, and we have such a set there, again, an example of such a set is a horseshoe, as I said in the beginning, and a hyperbolic horseshoe, then the barcode entropy is greater or equal to the topological entropy restricted to that set. Okay. So in particular, it's going to be positive whenever this thing is positive. Okay. Okay, so I have some remarks more like these conditions on the theorem. So hyperbolicity, local maximality, these are all, maybe the key thing to know for us is that these are common objects. It's not some, out of the blue thing for a map to have such a thing. And in dimension 2, they always exist. And in fact, the entire entropy, as I said before, comes from such sets. Okay, but if you want to be really sort of get into the details of this thing, people write papers about when hyperbolic sets are locally maximal, etc. It's a different subject topic, but they are independent conditions. I wanted to sort of acknowledge this. Finally, we have the next theorem, and the next theorem says that these two sort of concepts coincide in dimension 2. So if you have a closed surface, the barcode entropy and topological entropy are the same things. Okay. Okay, so what I would like to do is, here what I did is included this slide about this condition of locally maximal hyperbolic. I just wanted to tell you what it actually sort of give you like a summary of what it does in this picture. One of the key things about this whole requirement is that we can apply the so-called Amnesof closing lemma. And what it says is that if you have an approximate k-periodic orbit, which is in dynamics, this type of things are called epsilon pseudo-orbits. So approximate meaning it will be close to being a periodic orbit, but it won't be exactly one. So this lemma says that if you have an approximate k-periodic orbit, then in a neighborhood of the hyperbolic set, then actually there is a true k-periodic orbit nearby. And if you also assume the local maximality, this true orbit is in fact in the hyperbolic set. Okay. So we use this to obtain an energy lower bound as follows. Hopefully I'll get to tell you a bit about the proofs and this will enter the picture. So again, we have this locally maximal invariant set. And if we have a Floer trajectory, which is asymptotic to a k-periodic orbit whose initial condition is in k, then the energy of such a trajectory is bounded from below by some constant which is independent of the map, independent of the iteration order. So you have this lower bound, positive lower bound for the energy if you approach such an orbit. Okay. So what does do these things such sets, these requirements by us. Again, as I said more than once, all entropy comes from such sets in dimension 2, which is important in obtaining our theorem C, that in dimension 2, the two entropies are the same, the H bar and H top. And again, another important thing is the hyperbolicity. Here you don't need local maximality, but for an hyperbolic set, the topological entropy for this hyperbolic invariant set, it actually comes from growth rate of periodic orbits in the invariant set. So these are all like key effects that are used in the proofs of these theorems. A few, let me say a few words about, there are several things that need to be said, of course. For example, one of which, as I've already said, we absolutely have to work with all homotopy classes of paths, because it's really easy to construct an example where you have, all the topological entropy comes from non-contractible sources. And so H bar will also be positive. For instance, you can do it on a surface, but it won't, if you were to just stick to contractible periodic orbits, you would never see this positivity. So this is number one remark. I mean, my slides are dense. I wrote a lot of things here, but in essence, these are like easy to construct such an example. And of course, the next thing I should say is all this, I said already maybe a bit in the beginning of my talk, one of the sources of positive entropy is topological behavior of the map phi. And one way is the exponential growth of free homotopy classes, which are populated by orbits. And there's lots of, this is a rich topic. So I try to include at least the relevant sort of work here. I would like to acknowledge all kinds of work has been done. Although these are really different kinds of, a very different perspective. Our perspective is very different. So in these cases, you really have some kind of a robust feature like growing of fundamental group, things like that, or some kind of homology growth. And in our case, this is certainly not what is going on. So in our theorem, it's not the source of where this entropy is coming from. Okay. So, right. Okay. So, theorem C is very nice, right? We're just saying that in dimension 2, H bar is the same as H top. So one may ask, like, okay, isn't it great? Like, why can you have this in general? It's a very natural question to ask, and one should be aware of the fact that you can't actually expect this. So the picture is such that the picture is the following, basically. In higher dimensions, the growth of periodic orbits and topological entropy connection is actually weak. So it's really possible to have zero entropy map, yet exponential, super exponential growth of orbits. And on the other hand, it is also possible to have something which has no periodic orbits and have positive entropy, right? You can just take the product of a positive entropy map and take, I don't know, an irrational translation of the torus, for instance. The resulting thing still won't have any periodic orbits, yet will have positive entropy, because the entropy of the sound will be the sum of the entropies coming from each piece. So, and in dimension 2, it is actually essential that we actually capture these things all from all the periodic orbits. our naive conjecture is that it should be still true, C infinity generically in all dimensions, but of course, we don't know. Yes, this is more about the growth effect action spectrum. So I just wanted to hear, there are more natural things one could consider, such as why don't you look at the action spectrum, etc., or like other features coming from Floer complex like spectral invariants, etc. But you see, the thing is that in most cases, these things do not grow exponentially. Like, for instance, if you take a hyperbolic symplectic, the hyperbolic thing, take the surface of higher genus, for example, the diameter of the spectrum will grow linearly. So none of this is going to capture as a result of topological entropy. So this, what seems to be a more sort of natural things to look at, don't actually work. And finally, as I said before, there's a lot of previous work approaches to this type of entropy, topological entropy, from really different approaches, I should say. For instance, the entropy coming from this entropy for red flows, maybe it goes back to, I should say, Maccarini and Schlenk back 10 years ago, and then of course it's been sort of mastered by Alves and a lot of collaborators like Maives, etc. So in all these works, what you give is you give a lower bound for the topological entropy in terms of some kind of homology growth. Rep Floer homology, for example. This is all like, I would say, far-reaching generalizations of the more classical things from like geodesic flows, where you have, like in the hyperbolic case, for instance, you can bound the entropy from below by the growth of fundamental group, or so-called fundamental group entropy, for example. But it's an extremely interesting stuff and extremely non-trivial stuff. But the idea there is still seems in the background, there is some homology growth. And in what we are doing is we're looking at these compactly supported Hamiltonian diffeomorphisms. There is no homology growth. So this is kind of one key difference. I think that should be sort of emphasized here. Okay, so of course, one can also focus on in dimension 2 here. A lot more is known in dimension 2. Again, there are very recent works of, there's previous work too, but there are very recent works of Alves and Maives, Chor and Maives, all of them. For instance, in the most recent work of, okay, I don't know if it is the most recent, but it was in December, so. Alves and Maives, what they do is they prove the Hofer lower semi with respect to the Hofer distance, lower semi continuity of the topological entropy in dimension 2. And again, this is, or again, there is this notion of forced entropy, oftentimes existence of a certain type of orbit forcing the positivity of the entropy here. And there are also other works like Familiar, Hanevsky. They all give lower bounds for topological entropy in terms of the symplectic topology of the Lagrangian. Lagrangian and its Hamiltonian image. Okay, so, and I think maybe the one thing that is awfully interesting here is like we have these results which work in higher dimensions, but to this point we are not able to reprove any of the results of this type in dimension 2. Sort of, it is there is something going on there, something to understand, but it's sort of, at the moment, it's not clear what this is. So I would like to, of course, talk to you a little bit about the proofs of these results in the remaining 15 minutes. So let me start by the quickest of all, which is the proof of theorem C. I just brought the theorem back here, so by now you might have forgotten it. So what this theorem says is that for a closed surface, we have the barcode entropy equal to topological entropy. So this proof is boils down to actually 3 key ingredients. 2 of these ingredients is our second theorem. Let me just scroll here. The second theorem gives us this lower bound for H bar by the restriction of H top to our locally maximal hyperbolic set. And this corollary is the absolute, the same lower bound for the absolute entropy. But the most important, well, a fundamental half of this proof relies on Kattok's work from 1980, which says that in dimension 2, effect that I have already told you, you can calculate the topological entropy by basically focusing all hyperbolic locally maximal sets for your phi. Okay, so it is the supremum of this. Once you have this and combining these things, proving theorem C is just immediate, basically. Theorem B is, theorem B is the one that we have a lower bound in particular, giving us the positivity of the entropy by the topological one. So here, what is going on is to prove this theorem, we have like 2 key ingredients. Let me just scroll down and then I'll come back. One of them is the energy control. I already told you a little bit about this when, if you remember, I brought up this Amnesof closing lemma and all of this. This is where all of these things sort of brought together in the proof of this theorem. So one of them is hyperbolicity and energy control, and the other one is the fact that the tails of these barcodes for points in our invariant state are kind of energy isolated. So this is more like an algebraic result, I should say. So anyway, going back, so here's a key fact, which is easy to prove. Is let's again, throughout I'm in the setting of this theorem, I have my locally maximal hyperbolic set. Let's take a Floer trajectory. And the key fact is that if it has sufficiently small energy, then U of Si is a pseudo-orbit for phi. As I runs through, remember I'm looking at K periodic orbit, as I runs through integers mod K, okay? So what this means is that, as I said before, you look at U of S plus I, U S I plus 1, it is close to phi of U of Si, okay? And this closeness, the error is independent of the order of iteration, okay? So, you know, the proof of this is EU small gives you small derivative, and it in fact follows from some triangle inequality or something. It's not hard to prove, it is important though. So then what happens? So in the first step, we have our energy control. Again, we are in the same setting here. Let's take 2 periodic orbits, one of which has the initial point in K. Then the energy of the Floer trajectory is bounded from below by a positive constant, which is independent of the iteration, unless it can be possibly 0, okay? So to prove this energy bound, we look at 2 cases. One case is that, well, it's quite possible that the other end of the, of the Floer trajectory is also in K. Another case is that it is not in K. So if it is outside, then that means that this Floer trajectory enters a neighborhood of this point and enters this invariant set, and this is expansive. So in other words, this is more like somewhat older result of Viktor and myself, that there is a certain energy that you have to acquire in order to be able to cross a neighborhood, if this is outside. So this is where it follows, where this case follows. And it is used the fact that this having this isolating neighborhood is key here. An example is, for instance, if you have a hyperbolic fixed point. The second case is that the other end may be actually in K. Okay. In this situation, this is the situation where we use Amnesof's Amnesov closing lemma, and this is how we obtain this proposition. What happens is that when you have this, the other end of the thing is in K, we have actually our periodic orbits in K, right? It is in sort of invariant set, maximal invariant set. So then let me go back to this key point here. If we sort of, for small energy, I already told you that we are going to have this U of Si giving us this pseudo orbit. What the Amnesov closing lemma is going to tell us is that for the pseudo orbit, in fact, there is a unique true orbit, and it is going to have to be in this neighborhood that we are interested in, okay? Because we are in the locally maximal hyperbolic case. And then we have this, moreover, actually this orbit is unique and sort of depends continuously on the R variable here. Let me scroll back here, there is the S here. And in fact, it needs to be, by this uniqueness, it needs to be constant in S. So we're going to have this true orbit. On one hand, it will be equal to X. On the other hand, it will be equal to Y, but it will be also constant. So it will tell us that if this energy is small, then in fact, the two orbits have to be the same, which will mean that the energy is going to be zero. Okay? So therefore, I mean, as I said, this closing lemma is important, and this is what gives us this proposition. In this case, there are these two cases. Okay, so yeah, it's a bit technical, but anyway. So you have this proposition. So we now need a more on the algebra side of the story. What's going on here is that we are back to our barcode situation, and let's call something a Floer graph. It will be a directed graph where the vertices will be fixed points and the edges will be our bars, basically. If something enters the boundary of X, then I will put a sort of, this is X, this is Y, I will put an arrow from X to Y, and these arrows will be actually decorated. So it's possible that I have such a bar, such an edge, but I also have such an edge corresponding to maybe Y connecting to capped X, things like that. And the length of the arrows are going to reflect this situation, and the cappings and all of that will enter the situation. So, but again, one can essentially, this is the action difference, the length of an edge. So here's a proposition, as I said, more along the lines of algebra, is that if you have an epsilon, let's call a vertex epsilon isolated, if the length of anything that's coming in or getting out of that vertex is length greater than epsilon. And if your Floer graph has p many epsilon isolated vertices, then the epsilon barcode has to be at least p half in this case. Okay, again, think of the points in our hyperbolic set as the endpoints of such things, and there is, and as I said, they are energy isolated. So to put this all together, what you do is you let P of K to be the K periodic orbits in our invariant set. And by what I said above, then again, because of their energy isolation property, they satisfy by the second proposition that the epsilon barcode entropy coming from phi to the k should be at least p to the k, p of k over 2. And now we use the fact that for hyperbolic sets, the growth of periodic orbits, exponential growth of periodic orbits actually gives us the topological entropy. So we have this equality, and it is bounded from above by the barcode entropy as the result. So which is the proof. And I have a bit more time to also touch upon the proof of the first theorem. Remember, the first theorem gives actually this upper bound for the barcode entropy. The path for the proof follows a much more traditional route here. It goes through the Yomdin theorem, which gives us a lower bound in terms of the exponential growth of volumes. So the idea of the proof is as follows: exponential growth of the epsilon barcode entropy implies the volume growth of Lk. Here, Lk is the kth image of L under our phi. And in turn, this gives us the positivity of H top. Okay, so let me touch upon quickly how this works. So how am I going to get this, this thing? So to do this, we construct something we call like a Lagrangian tomograph. So let's start with the Lagrangian, closed Lagrangian submanifold that's just fixed an epsilon. And a tomograph will be a map which goes from some ball of d-dimensional, possibly big d-dimensional ball times this n-dimensional Lagrangian submanifold to our manifold M. And we want this map to satisfy the following properties. We want it to be a submersion onto its image. And for each S, so ball B is this is where S's are from. This is my parameter domain, okay? So psi sub S are going to be, the image of psi sub SL are going to be my L sub S's. And they will be smooth embeddings, starting with the identity. I already said that the images will be also, I didn't say that they will be Lagrangian submanifolds, and they will be Lagrangian submanifolds of M, which are Hamiltonian isotopic to what I started with. And then they will be epsilon half close to what our beginning Lagrangian submanifolds. Such a thing exists for any sufficiently small epsilon and any closed Lagrangian. So the way you get this Lagrangian tomograph is simply you just take a tubular neighborhood of, identify a small tubular neighborhood of L in M with the cotangent bundle, and then these psi sub S are going to be obtained as the graph of exact one forms for some functions on the Lagrangians. They will all be parameterized by S. And the fact that, so if your epsilon is small enough, if all this action is going to be happening in a small neighborhood of the zero section, so we will get all the closeness and Hamiltonian isotopic and everything. And the dimension of the ball, of course, will come into the picture because we want transverse intersections. We want this to be a submersion psi. And we can just add in as much as needed dimension there to achieve this. And we will certainly need some dimension because of the Lagrangian intersections property. So, okay, so a bit more on the details, like the last two slides here. So let L tilde to be a closed n-dimensional submanifold. Let me set n of S to be, so I have this tomograph now in the background picture. I started with L, I constructed my tomograph, and I look at now the intersections of L twiddle. L twiddle is some other Lagrangian submanifold here. The way everything is constructed, this is going to be finite almost everywhere, for almost all S, and it will be integrable. So then we have the following lemma, which is what we call Crafton's inequality. So you integrate this function over the ball, and it's going to give you an upper bound on the volume of L tilde, Riemannian volume of L tilde. Now, again, for this lemma, you don't need this Lagrangian condition on the tomographs. This is a, standard construction. Such objects in this type of thing is standard in integral geometry. It's similar to like calculating if you have take a closed, what is the Crafton's equality? If you take a closed curve on the plane, for instance, you can calculate its length up to a constant by intersecting it with all lines and then affine lines, and then you just integrate this intersection, basically. So this is similar to that, but we don't have an equality in this case, of course. One cannot, because we're really intersecting with a particular type of submanifold which come from like graphs. In any event, this is standard to prove once you have your tomographs. So now let's apply this picture. I'll be done in 2 minutes probably. So I start with L tilde, so I want to just apply it to my L to the K situation. I'm going to look at the KL. And so my intersections NKS will come from LS intersected with L tilde. And again, the way the tomograph is constructed, LS will be transverse to L tilde almost everywhere for almost all S. Things will be they will be sufficiently close to L in Hofer distance. And as I said in the beginning, our barcode is going to give us a lower bound for these intersections. So then what you do is to calculate the volume of LK using Crafton inequality and the fact that barcode gives you a lower bound for intersections. You just, this is greater or equal to up to a constant, this integral, and this is greater or equal to epsilon barcode, or 2 epsilon barcode, to be precise. And then you just take the lim sup everywhere, and use, of course, using the fact that, let me go back, the Yomden theorem gives us volume as a lower bound. So let's go back. So this is where the H top comes into the picture. The first part from here to here is Yomden. And the rest is definition, pretty much. So, and again, I want to emphasize that it really doesn't matter in this whole picture what the Lagrangian formology is. It can be 0, really. It's all we want, however, is that it should be defined. And thanks for your patience. And I think that's the end of my talk.
Great, thanks so much. Let's give Basak a round of applause. Are there any questions for the speaker?
Yes, I have a question. So you mentioned that this equality of this topological entropy and the Floer theoretic one for Riemann surfaces, is there an analogous result for contact 3 manifolds?
For the equality, I don't think so. I don't think so. I mean, anyone in the audience, if anyone knows, please add, but I don't think so. Yeah, I don't think so.
Maybe I can add a word on that. Excuse me. as such, this machinery, this theory does not quite yet exist for contact for rep flows.
Yes.
Actually, I have a former student who is looking into it. Out of 3 theorems, probably theorem A, the lower bound in one direction, will probably work. Theorem B,
Sorry about that.
there is a big problem with theorem B, the bound in the other direction. Namely, kind of, we don't know how to do the energy control.
Yes, yes.
There is like a non-trivial part that which we have not know, which we've been thinking about for a very long time, like 10 years by now, which we don't know how to do. So there is a problem there. Which is an obstacle to one problem with the equality, right? You don't have the inequality going in the opposite direction. You have only one of them.
Yes.
And finally, there is also this fact that all entropy is coming from hyperbolic sets in dimension 2. This should probably be true for rep flows or even for flows in dimension 3, but I am not absolutely sure. So this one would have to ask someone in dynamics about that. So in any event, the whole machinery should somehow extend to the rep setting to the in all dimensions, but probably it won't work as nicely as in this case.
Thank you.
Yeah, I had a related question, which is maybe just sort of like a confusion. So I guess I was just wondering if if you wanted to get a lower bound on the topological entropy for like a ray flow, let's say on S3, so it sounds like probably if you could define the same barcode entropy for something like some sort of contact homology or symplectic homology of.
But that's sorry. Go ahead.
Oh no, sorry. Go ahead. Yeah, I have more, but yeah, go ahead first.
No, what I wanted to say, yes, indeed, there are such things. Like for, if you have this sort of growth of some kind of homology theory there, yes, you can get lower bounds, I think.
So wait.
But using a sort of different. Sorry, go ahead. Yeah.
No, but I'm talking about H top. No. Go ahead, Victor. Maybe I'm misunderstanding.
I'm just saying, like, speaking about rep flows are more similar to symplectomorphisms than to Hamiltonian maps, in the sense that many things can happen. First of all, you can have just homological growth. The size of the symplectic homology, the dimension, can grow with the action, can grow exponentially with the action. So that's something does not happen in Hamiltonian Floer theory. Like when you have a Hamiltonian diffeomorphism, no matter how many times you iterate it, the Floer homology will remain the same. So this theory, in the rep case, when there is homological growth, the theory is quite well developed by Alves and his collaborators. So there is like a lot is known how to get topological entropy from the growth of various type of symplectic homology. Here, the situation, this work is about a different thing. Here, we don't have growth. So it can be like, for instance, the rep flow on the standard contact sphere, where the homology a priori does not grow. So I think, again, one can develop this theory and one can prove an analog of theorem A, but probably theorem B will be already very difficult. I expect sort of this to happen within a year. Someone is like looking into that, so this part should work, but it probably won't be as sharp as the Hamiltonian case. I'm not sure if I answered the right question.
Yeah, I guess what's confusing me a little bit is like the rate flow at an S3 sort of looks a bit more like an autonomous flow of a Hamiltonian algebra.
Yeah,
so which in that case, so is that just saying that there's sort of some subtle thing where you can't think of it as a limit of autonomous Hamiltonians, because then you would think you just get zero entropy, but
the rep flow is certainly in this class. Yes, yes, indeed, it looks more like a Hamiltonian diffeomorphism, like on the standard ST.
Yeah.
Yeah, it's.
But you see, the entropy for autonomous things in higher dimensional is not zero. Maybe that's the confusion.
I see. That was just a statement in that was just in.
It was a
dimension
two-dimensional statement.
Oh yeah, okay. If
So
that's the question, yeah, it is certainly autonomous, but
yeah, it's not true. It's not true that in higher dimensions H top is zero. No, you have room a lot of, and this is all these things indeed are. It's not. It's a two-dimensional phenomenon, and you just don't room for any interesting dynamics. You either have rotations on regular levels, or things like that. It's not like
I see. So in principle, one way to extend this to like a rate flow in S3 would just be take sort of Hamiltonians which look kind of roughly zero in the interior of some star-shaped domain, and then sort of large outside, and then define the barcode entropy for the Floer complex exactly as you did, and then just sort of take a limit as the Hamiltonians look more and more like a kind of zero in the interior.
And probably it will work. Like the first part, theorem A will probably work like with some.
Okay, thank you very much.
But as Viktor said, theorem B is already going to be very difficult, at least because of the energy bound. Yeah.
Right.
Anything else?
You have a question in the chat from BumJoon Sohn. For given phi, is there possible inequality between absolute barcode entropy and relative barcode entropy?
For a given phi,
yes, this is about the variational principle. It's conjecturally yes, but we don't know. There should be.
Yeah.
Great. Are there any further questions for the speaker? Okay, well, let's give Basak a round of applause for a fascinating talk. Thanks so much.